we are going to look at lesson 6 in the course IT 2403, that is systems analysis and design. In this lesson we are going to look at the systems design. We have looked at problem identification, we have looked at analysis, and now we get on to the systems design. In this stage what we really do is we produce a design specification for the new system. This is also known as a physical design, and here we design the inputs, outputs, files, databases and other computer based components. So, during the analysis what we did was really emphasize on the business problem, that is we identified what the problem was and we found alternative solutions and so on. Now, we are trying to implement the solution. So, in the design stage what we do is emphasize on the technical or implementation concerns of the system. That is what kind of technology we are going to use and also how it will be implemented. There are several system design approaches in practice today. Modern structured design, information engineering, prototyping, JAD, RAD and object oriented design. So, we will look at each one of them in this lesson. First, if we look at the modern structured design, you can see there is a, in the diagram you can see there is a process A, and that process A will get broken down into process A1, A2, A3 and A4. Then again if you look at the process A1, it can be further subdivided into process A11, A12, A13 and so on. So, this is a process oriented technique for breaking up a large program into a hierarchy of modules. So, why we say break it up into a hierarchy of modules is because if you take a big problem, it may be difficult to give the solution to a big problem. But if you break it into components of smaller problems, then each one can be separately implemented and solutions can be found for these separate components. So, finally, when you have implemented all the small modules, finally your big program will be implemented. So, this will result in a computer program that is easier to implement and maintain. That is, maintain means whenever you want to do changes. Now, synonyms or alternate names for this modern structured design are top down program design and structured program design. And this is a technique that decomposes the system's processes into manageable components. So, you have these big programs which you break into smaller components. Only thing, these components or modules should have the following properties. Modules should be highly cohesive. Cohesive means each module should accomplish one and only one function. That is, you must not combine more than one function in a single module. Basically, it should when it is implemented, it should accomplish only one and only one function. And modules should be loosely coupled. Loosely coupled means there must not be a lot of dependence among these modules. Each one must be minimally dependent on the other module. Why you do all these things, that is, this highly cohesive and loosely coupled modules are implemented, because in the long run when you have to maintain these programs or do changes, doing changes will be much easier, and also when you do changes to one component, it will not trigger errors into the other components. And modules should be adaptable. Adaptable means it should be easy to incorporate changes, and modules should be understandable. Each module taken on its own or each component taken its own should be understandable to the person who is reading the code or the comments in the component. To continue with the modern structured design, a technique that is used is in this methodology is the structure chart. This is a software model derived from structured design. it is derived by studying the flow of data through the program. So, this is a data driven technique. So, if you look at this diagram here, you have a module or a component called calculate sales total having the number 1.2, and this 1.2, the module calculate sales total, actually has been divided into 3 components or 3 sub modules. There is 1.2.1 get sales transaction, 1.2.2 adds to total, 1.2.3 output total. So, you can see that we said when you modularize or when you break into components, these modules or components should deal with as much as possible only one function. So, if you look at this module called get sales transaction, basically it does only one thing. It accepts the sales transaction details into the system and then adds to total. So, all these sales transactions that are entered have to be accumulated or the total must be found. So, this 1.2.2 module, what it is doing is it is preparing the total, and the total is again passed on to another module called the output total, which has a number 1.2.3, and the function of that module is outputting the sales total. So, this is how functions are divided among these modules. And then we also talked about loose coupling. Loose coupling means they are not dependent too much on each other. So, if you look at this, now this calculate sales total gets only one thing from the sales transaction, get sales transaction module. It gets the details of the sales transaction, nothing else, and then it passes this sales transaction to 1.2.2 adds to total. So, each transaction that is taken is passed on to this module, and the function of that module is totaling all these transactions. And so you can see this symbol, there is a arrow, curved arrow, curved line with an arrow which indicates a repetition in this case. So, it is repeated means number of sales transactions have to be added together to get the sales total. So, once the final sales total is obtained, that would be passed on to the module 1.2.3 to output the total. So, you can see how the modularization has been done. And one important thing in this is what is called the parameter passing. So, we will look at the parameters that are passed from each one of these modules. 1.2.1 passes the parameter called the sales transaction to calculate sales total. Then the sales transaction is passed on to the module called adds to total. So, these are the various parameters that are being passed. So, here the calling module passes a set of values to the called module and receives a set of values in return. These values are passed as parameter values. So, the example, a value of sales transaction is passed from module get sales transaction to module calculate sales total. Module calculate sales total then passes the value of sales transaction to module add to total and get a value for sales total in return. The value of sales total is then passed from module calculate sales total to module output total. So, the connection between modules is kept only via this parameter passing. There are no other ways in which these modules are connected to each other. And the execution sequence in this structure chart is by convention, modules are executed from left to right in each level. So, if you look at this example again in the diagram, the execution will be from left to right. So, first 1.2.1 will be executed, followed by 1.2.2 and then followed by 1.2.3. Here we have a structure chart which has only 2 levels. There may be structure charts with more than 2 levels. So, in that case, the lowest level will be executed from left to right first and then the next level and so on. In the given example, module get sales transaction is called before module adds to total. Module output total is the last module to be called. Certain conventions are also used to represent decisions and repetition. So, when we look at this diagram, again I told you about this curved line with an arrow that indicates a repetition, because there will be a number of sales transactions which have to be added together to find the sales total. So, the repetition, because in a computer program we know that steps are executed in sequence, but also sometimes we have to branch out to certain instructions, and certain instructions have to be repeated. So, repetition is shown, the decisions we will discuss how the decisions are made occur whenever a calling module has to decide to call only one of a number of modules. Look at this example given here. Here there has to be a decision made. The payment, if you look at, payment can be made either by cash or check. When you make a payment, a single payment, you are not going to pay it both by cash and check. It will be either made by cash or made by check. So, in that case, how do we show this in a structure chart? You can see this diamond shape below the box called payment, that indicates the payment will be made either by cash or check. So, the decisions or conditions are shown by a diamond. The repetition occurs when some modules are called repetitively by the calling module. So, in this first diagram that we saw, calculate sales total has to be done a number of times. So, to calculate the total, how does it do? All sales transactions have to be added to the total. Each and every transaction that has been input through get sales transaction will be added to get the adds to total. So, that is why the repetition there, and it is shown by a looping arrow. Structure chart is a technique used in modern structured design. The objective of structured design is to produce a good design. Then another method used in designing, we said, is information engineering. This is a model driven and data centered but process sensitive technique for planning, analyzing and designing information systems. Primary tool of information engineering is a data model. We have looked at this ER diagrams, or what we call the entity relationship diagrams. So, the primary tool of information engineering is the data model or the entity relationship diagrams. Involves conducting a business area requirements analysis from which information system applications are carved out and prioritized. Then another technique is the prototyping. Again, we have discussed this in a previous lesson, how the prototyping advantages, disadvantages and so on. This approach is an iterative process involving a close working relationship between the designer and the users. So, especially this technique can be used when there are certain ambiguities, or it is difficult for the designers also to straight away get at a final decision, because you will start with the prototype, show it to the users and then get their comments, and then maybe do some modifications to the existing prototype. So, this can be an iterative process, and always the designer and the users will be participating in this process. The key benefits of prototyping is encourages and requires active end user participation. So, end users are always involved when we do the prototyping. Iteration and change are a natural consequence of systems development. So, because why we say it is a constant change, because at the beginning the end users also do not know exactly what they want. So, when they see something only, they will be able to decide whether that is what they want or whether they want something different. So, if they say that they want something different, the designer can change the existing prototype and then show a new prototype. So, the new prototype again will be presented to the end users, and they can again suggest any changes or modifications to the prototype. So, that is why we call this a iterative or repetitive process, and in every iteration you may be doing some changes. So, prototyping endorses a philosophy that end users will not know what they want until they see it, because when they see something only they will be able to decide whether that is what they want or whether they want something different. Prototypes are an active model that end users can see, touch, feel and experience, because prototype is something that is existing. It is not something that is on a piece of paper as a diagram. This is something that they can really experience, work with it, touch it, see, feel and experience. So, an approved prototype is a working equivalent to a paper design specification, with one exception: errors can be detected much earlier, because the prototype is a actual working model. If there are any errors or anything like that, it can be detected much earlier than if you were working with a paper design. Prototyping can increase creativity because it allows for quicker user feedback, which can lead to better solutions, because the users are the people who really know what they want, and they also may have ideas of how these solutions can be implemented. So, when they see a prototype at actual work, they will come up with certain solutions, and sometimes they may be better solutions than what the designer can propose. Prototyping also accelerates several phases of the life cycle, possibly bypassing the programmer, because most of the prototyping languages, the languages that are used in prototyping can be used to generate the code. So, you may bypass the function of the programmer altogether. Just as much as there are advantages, there are also disadvantages in the prototyping technique. This can encourage ill-advised shortcuts through the life cycle, because when you show a prototype to the end users, they might feel that this is a good solution and this should be acceptable without any changes. But we must realize prototype does not have the necessary designing techniques incorporated into it, because this is not just producing a solution. It must be, we have to keep in mind that it is one of the best solutions, but also which can be used for a long period, which should be adaptable, which should be we should be able to do changes into this from time to time. So, therefore, the prototype is not the best solution to implement. Later on, we have to the various stages in life cycle that we have used, like testing, all those stages have to be applied to the prototype as well. So, the comments have to be incorporated into this, and the diagramming has to be done, and later on we must think about this as a system which has been built on good systems analysis and design techniques and also software engineering principles, so that later on the changes or modifications can be done easily. But this is not understood by the users, because what the users want is something that at the moment. So, they do not realize that this is not a good product. No, it has not been designed properly according to the principles of systems analysis and design and software engineering. Therefore, we have to make the end users understand that prototype is just like a model only, but it is not the real thing. Then in joint application development or JAD technique, this also emphasizes participative development among system owners, users, designers and builders. So, all these people get together in this joint application development process. JAD sessions for systems design, usually there will be a systems designer, role of facilitator for possibly several full day workshops intended to address different design issues and deliverables. So, the designer will play the role of the facilitator. Then and where we said all these people will participate in the sessions, that is system owners, users and builders, the designer will be the facilitator. Then the RAD or rapid application development is the merge of various structured techniques, especially the data driven information engineering with prototyping techniques and joint application development techniques to accelerate the systems development. So, rapid application development is a combination of the previously discussed techniques, so that the development process can be accelerated. RAD calls for the interactive use of structured and prototyping to define the user's requirements and design the final system. Using structured techniques, the developer first builds the preliminary data and process models of the business requirements. Prototypes then help the analysts and users to verify those requirements and to formally refine the data and process models. So, first you will use the structured techniques followed by the prototyping. Then object oriented design is the newest, the most recent design strategy, and it is used to refine the object requirements definitions identified earlier during analysis and to define design specific objects. Based on the design implementation decision during object oriented design, the designer may need to revise the data or process characteristics for an object that was defined during systems analysis. So, during analysis you may have identified certain objects, but during the design process you may refine them some more. Then there are certain, whatever the methodology or the technique that you use, there are certain design tasks, that is whether you use prototyping or joint application development or rapid application development or structured techniques, there are certain tasks that you have to perform. These are the 5 things that you have to do. You have to design the application architecture, design the system's database or databases, design the system interface, that is how do the users interface with the system, package the design specifications and update the project plan. So, we will look at one by one. The application architecture defines the technologies to be used by and also used to build one, more or all information systems in terms of its data, process, interface and how these components interact across a network. It serves as an outline or blueprint for detailed design and implementation. So, the application architecture really looks at an information system in terms of the data that is involved in this, what are the processes, the interfaces and how these components interact across a network, because today most systems are really networked systems. The primary tool used in this is the physical data flow diagram. So, we will now look at some of the symbols that are used in physical data flow diagrams and how they differ from logical data flow diagrams which we drew or used in the analysis stage. So, physical data flow diagrams model the technical and human decisions to be implemented as part of an information system. So, remember we had processes. Now, if you look at the difference between a process in a physical data flow diagram and a logical data flow diagram, they communicate technical choices and other design decisions to those who will actually construct and implement the system. So, if there is a process diagram, then the symbol will have to contain an ID. It may be optional or it may have to be there. Then there is an action verb combined with a noun or object phrase, and there is a implementation mechanism also has to be there. So, as an example, we will look at actually in the textbook you will be able to find some examples here. It is very important that you look at sometimes you may write here with how it is implemented, who is doing it, all those things will be written here, unlike in the logical DFD process. So, I suggest that you look at this in the textbook and look at how you draw a process in a physical data flow diagram. So, a physical process can be either a processor, that is a computer processor, the CPU in the computer, or it could be a person, or it could be a technical implementation of specific work to be performed, such as a computer program, or it could be even a manual process. The process, now in the logical data flow diagrams, we didn't mention any of these things in the process. It just said what the process is, but it didn't indicate how you are going to do it or who is going to do it. But in the physical data flow diagrams, the process must have who is going to do it, whether it is the CPU going to do it, or whether it is a person, whether it is done by a computer program, or whether it is done by a manual process, and so on. So, characteristic of physical DFDs: logical processes may be designed, may be assigned to physical processes such as PCs, servers, mainframes, people, or devices in a network. A physical DFD would model that network structure. Each logical process must be implemented as one or more physical processes, as some logical processes must be split into multiple physical processes. So, in a logical data flow diagram, you could have only a single process may get divided into one or more physical processes. It is not necessarily a one-to-one map from the logical to the physical data process. Then the physical data flows represents any one of the following: planned implementation of an input or output from a physical process, a database command or action, that is like create, read, update or delete, import of data from or the export of data to another information system across a network, flow of data between two modules within the same program. And the physical data flow representation is, again you have to write the implementation method, and like example, printout, salary equity report. This also you can refer to figure 13.2, page 482 in the reference 1 to learn how to apply one of these naming conventions in the physical DFDs. Then the physical external agents, no change from logical DFD to physical DFD. That is because external agents were classified during systems analysis as outside the scope of the system and therefore not subject to change. So, the only thing that does not change when you convert from a logical DFD to a physical DFD is the physical external agents. Only a change in requirements can initiate a change in external agents. Of course, the only way you can change the external agents is either the requirements, more requirements have been added into the system, or some other requirements have been removed from the system. In that case, if more requirements have been added, then maybe you will introduce more external agents. But if some requirements have been dropped out, then certain external agents may be removed from the scope of the system. The other symbol in the physical data flow diagrams that we need to discuss is the physical data stores. This represents the implementation of one of the following. So, in a logical data flow diagram, which didn't say how it is going to be implemented, but here we have to say how it is going to be implemented. Is it a database, or is it a table in a database? Is it a file, computerized or non-computerized? Is it a tape or media backup, or is it a temporary file like transaction files like tax tables and day-to-day transactions and so on? Then how do you represent them? Again, you have to implementation method, data store name, ID is optional, or it could be the data store name and the implementation method. Again, the ID can be optional. So, some examples are given here. Now, purchase orders, that is the logical data store, we only say purchase orders, but when you convert into a physical data store, this will say the name is there, but also how you implement it using MS Access. So, that is the difference between the physical and the logical data stores. So, once you have done that, then you have to design the system database. Now, databases are a shared resource, that is not only used by one person, but it may be used by a number of persons. A database should be adaptable to future requirements and expansion. Also, when we design a database, we must measure how it is going to expand and cater to those expansions. Issues to be addressed during database design include how programs will access the data, programming data structures and their impact on performance and flexibility. We have different data structures like queues and stacks and so on. So, depending on how you implement these data structures, that will affect the performance and the flexibility. Internal controls to ensure proper security and disaster recovery techniques in case data is lost or destroyed. Because number of people are using the database, there have to be, you have to have the control measures. That is, as people's needs vary, they should not be allowed to access the entire database. Depending on their needs only, you need to give them access to the various parts of the database. And also how you are going to do backups and so on, because if data is lost or destroyed, there must be a way of continuity. Record size and storage volume requirements have to be calculated, because at the time you implement it, the record size may not be the same as when it is after certain years of use. So, these things have to be catered to. Purpose is to prepare technical design specification for the database. So, who will participate in this? Systems analysts participate in database modeling, system designers complete the database design, data administrator recognize that the new system most likely uses some portion of an existing database. So, that has to be taken into consideration as well. System builders build a prototype database for the project. The inputs will be the application architecture and distributed analysis decisions. Output or the deliverable will be the database schema. Now, designing the system interface, that is, once the application architecture has been designed, then the databases have been designed, the system interfaces have to be designed. Designer can work closely with the system user to develop input, output and dialog specifications. So, here it is very important for the designer to work closely with the system users, because this is going to provide the interface between the databases and the programs and the actual users. So, if the users find it difficult to use, then they will not be satisfied with the system. So, therefore, system users have to be consulted and they have to participate very actively in designing the inputs, outputs and the dialog specifications. The precise format and layout of the outputs must be specified. Internal controllers must be specified to ensure that the outputs are not lost, misrouted, misused or incomplete. The data capture methods for the input should be designed. So, when we say data capture methods, there are various ways in which data can be captured, like using the keyboard for data entry, or maybe using something like barcode readers in a POS system, that is point of sale system, or it may be a scanner is being used to scan the data, or it may be like in a ATM, that is a teller machine where you use a card, so magnetic data. So, different ways of data capture methods have to be considered. Editing controllers must be designed to ensure the accuracy of the input data, especially if the data is input through keyboards, then you have to think about how accurate the input data is, and those control measures have to be in place. Then for dialog design, the designer must consider terminal familiarity. That is, the people who are using these various terminals, that is the actual users, how much are they familiar with the various instruments that are being used, or the outputs that are used, or the dialogue. Sometimes people may be not highly educated people, they may be they may not understand if the dialogue is not simple, they may not be able to understand all that. So, possible errors and misunderstandings that the end user may have or may encounter, the need for additional instructions or help at certain points, the screen content and layout. So, here you have to really consider the level, the educational level of the users also have to be taken into consideration. Then who are the participants here? System users, system designers and the system builders. Once you have done all this, then you have to package the whole thing. Package all the specifications from the previous design tasks into a set of specifications. Guide the computer programmers' activities. If the programs have to be written, then you have to guide the programmers. Inputs, database input and output specifications have to be given. Then update the project plan. Re-evaluate project feasibility and update project plan. Project manager facilitates this task. Analysts and owners should consider the possibility that based on the completed design work, the overall project schedule, cost estimates and other estimates may need to be adjusted, because this is a point in the system development life cycle where you can rethink whether what you have done is sufficient, or whether you have more work to do in the form of designing, or whether you should go back to certain stages, or whether this is feasible at all. This may be another point at which all these decisions have to be made. So, the deliverable at the end of this should be an updated project plan, should include a detailed plan for the construction phase that should follow. So, it is immediately after this that you will actually go into the actual implementation or construction of the system. So, systems analysts must continuously read popular trade journals to stay abreast of the latest technologies and techniques that will keep their customers and their information systems competitive. So, analysts should be always abreast. They must always update their knowledge with the technological changes that are happening in the industry, because if you are not aware of all those new changes or new techniques that come into the market, your information systems may not be competitive. The information systems framework provides one suitable framework for understanding IT architecture. Today, information systems are no longer monolithic. Monolithic means single systems, mainframe computer based systems built on some combination of networks which are distributed. So, today the maybe 10-20 years ago we had systems based on mainframe computers, but today it is not so. So, we will look at these different types of systems like centralized systems, distributed systems, and then the different distributed systems, how they can be implemented and so on and so forth.